All right, we're going to do a epsilon delta proof of a limit to help us prepare for the quiz. If you wanted to look back at our notes from before, we have some other examples. This one's going to be a linear one. And with the linear one, we have a very kind of like straightforward approach. So I'm going to go ahead and set up the two parts that you want to start with for your proof. What we need is absolute value of x minus whatever we're approaching is less than delta. And so this is saying that if we are some small distance away from delta, and then the other thing that we want is for us to be a small distance away from our limit. And the way that we set that one up is with another absolute value. But inside this one, we put f of x minus the limit, and we set that one less than our epsilon. So these are the two parts that we need for our proof here. And so the f of x, that's coming from this part. And then the limit is going to be that 5. So here is my limit. And in red, that part is my f of x. Okay. So I'm going to go ahead and plug those in. And I have the absolute value of 1/2 x plus 3 minus our limit, which is 5. And I need that to be less than epsilon. All right. When we're doing the linear ones, what we're hoping for is that we can make this piece look just like our delta over here. So I'm going to go ahead and do some simplifying. And then look back over here and go, ooh, if I pulled out 1/2, I can see how I'm going to get that delta. Because 2 divided by 1/2 is actually 4. And so now I can see my delta piece right there. So I'm going to go ahead and divide both sides now by 1/2. Dividing by 1/2 is the same thing as multiplying both sides by the reciprocal of 1/2, which is just 2. So I'm multiplying both sides by 2. And I get absolute value of x minus 4 is less than 2 epsilon. Awesome. So that's telling me that I want to set my delta equal to 2 epsilon. So choose delta is equal to 2 times epsilon. All right. And this is our preliminary work for our proof. So I'm going to go ahead and now actually start my formal proof. And I'm going to say for any epsilon greater than 0, if delta is equal to 2 epsilon, then, and I want to make sure that my delta is positive, so I'm going to say that my absolute value piece is going to be between a 0 and the delta. So my absolute value of x minus 4 is less than delta, which was essentially what we wrote up here. I just didn't put the 0 over there, but I want to ensure that it's positive. So this is making sure that's a positive delta. So then having the distance between our x and the value 4 being less than delta implies that the absolute value of f of x minus the L is going to be, we ultimately want this to be less than epsilon. So I'm going ahead and I'm plugging in what we put down in our steps earlier up here, the 1/2 x plus 3 minus 5. And when we simplified that, that became 1/2 times the x minus 4. And at that step, I can go ahead and say that that's less than 1/2 times our delta value, which is going to be the 2 epsilon. Why am I doing that? Because at the end, I want this to say equals epsilon. So now what I can do is cross out those 2's and I can see that this is equal to epsilon, which is what I was hoping for. Okay, so I can either put the little box at the end to say that I'm done with the proof, or you can also put the 3 dots and say, so the limit as x approaches 4 of 1/2 x plus 3 is equal to 5. And so we've completed that one. And when we move on to ones that are not from linear functions, we use a lot of the same things, but we're not necessarily looking exactly for our delta value to be like exactly in the same place. Instead, sometimes what I do is I solve for the x instead, and then solve for the x over on this side, and then equate things that are on either sides of the inequality. So let me show you an example of that one next. Okay. How about we do a quadratic? So we're going to prove that the limit as x approaches 3 of x squared minus 1 is equal to 8. And it should be equal to 8 because 3 squared would be 9 minus 1 would be 8. So I'm proving something true here. And we're going to start with the same setup where I have the absolute value of x minus what we're approaching, the 3. And I want that to be less than delta. And the other thing that I want is our absolute value of the f of x minus L to be less than epsilon. And so for this one, my f of x is that part right there. And then I want to subtract the limit, which is this 8. So we want that to be less than epsilon. I'm going to go ahead and simplify this a bit. So this will be x squared minus 9 is less than epsilon. And so I can see that this is not going to be a thing where I get exactly the x minus 3 here. So instead, this is going to be one where I solve both of these for x. So I can start with either one. If I decide to go with the delta here, in order to take off the absolute value brackets, what I need to do is take the x minus 3 is less than delta on this side, and then put my inequality sign over here and put minus delta on the other side. So that lets me open up the absolute value brackets. And then if I want to solve for x, I would go ahead and add 3 everywhere. And so I have that my x is greater than 3 minus delta, but less than 3 plus delta. And if I drew you a picture of this, we would actually see that the deltas are not going to be the same distance. And so ultimately, I'm going to be finding which of the two deltas is smaller. So I'm going to go ahead and set that up now and just go ahead and say that this one is my delta 1 and this one is my delta 2. And we'll use that in a moment to help us do a simplification so I can see which one of them is smaller. All right. Now I'm going to pick up where I left off over here and get this solved for x in the middle by taking off the absolute value brackets again. So we're going to write x squared minus 9 is less than epsilon. And then I need to put negative epsilon over on this side. I'm going to add 9 everywhere. And so that's going to give me that x squared is greater than 9 minus epsilon, but less than 9 plus epsilon. And I'm trying to get x by itself in the middle. So if I take the square root, I would have square root of 9 minus epsilon on this side and the square root of 9 plus epsilon over on this side. And now we've got x by itself for each of them, which means that I can set these two left-hand pieces equal to each other and then these two right-hand pieces equal to each other. So I'll go ahead and circle these ones in red. I'm going to set this one equal to that piece and solve for my delta 1. And then I'm going to set this one equal to this piece and solve for my delta 2. And since they're not the same size, what I want is for the smaller of the two deltas. The smaller of the two deltas is going to ensure that my y values stay within my epsilon band. Okay, so I'm going to set 3 minus delta 1 equal to the square root of 9 minus epsilon. And if I'm trying to get delta 1 by itself, I can go ahead and add the delta 1 over here and then subtract this square root of 9 minus epsilon on this side. So I'll have 3 minus the square root of 9 minus epsilon is equal to that delta 1. And I know I skipped steps there, but I promise that's how that one will work out. And then I'm going to go ahead and set these two pieces equal to each other. So this is going to be 3 plus delta 2 is equal to my square root of 9 plus epsilon. And to solve this one for delta 2, just subtract 3 from both sides. Okay. And so I've got delta 1 and delta 2, and I want to choose which one is smaller. And so to figure out which one is smaller, if I don't have a graph to look at, if I just choose a value to plug in for epsilon, that's going to let me choose which of these two is smaller. And so my epsilon has to be a positive number. And I'm going to try and make it a little convenient on myself in a way that will make one of these square roots kind of nice. So if this was a square root of 4, that would be nice. So if I let epsilon equal 5, then for my delta 1, that would be equal to 3 minus the square root of 9 minus, and then I'm plugging in 5 for the epsilon, which would be 3 minus the square root of 4, which is just 3 minus 2. And so my delta 1 would be equal to 1. And so I'm not actually doing this to say my delta 1 is equal to 1. I'm doing this by plugging in the epsilon is equal to 5 into both of these pieces. It's going to let me determine which delta is the smaller one, and then I'm just going to use that. So I'm going to go ahead and plug in the 5 over here as well. So this is going to be 9 plus 5 underneath my square root minus 3. This side doesn't turn out quite as nice. This is the square root of 14 minus 3. And I don't actually know what that is without a calculator, but I do know that this value is smaller than 1. How do I know that? Well, if this was the square root of 16, that would be just 4, and 4 minus 3 would be 1. But this is not the square root of 16, it's smaller than the square root of 16. So this has to be less than 1. But if you did have a calculator, you can actually get a value for that. So I'll say that's approximately equal to 3.74 minus 3, which would make this definitely smaller than this one. So I did this in order to just figure out, is my delta 1 smaller or is my delta 2 smaller? And my delta 2 is the smaller one. So I'm going to come back up to my symbolic version of delta 2, which was this right here. And this is what I'm going to select for my delta when I do my proof. Okay. So I'm going to start my proof with, for any epsilon greater than 0, if delta equals, and I'm going to go ahead and put in my square root of 9 plus epsilon minus 3, then my absolute value of x minus, we said 3 is less than delta, implies that the absolute value of f of x minus L is less than epsilon. Okay. So we're good on that one. Or we could go ahead and put the 3 dots if we want. And we can say, so the limit as x approaches 3 of x squared minus 1 is equal to 8.